Hello friends, welcome to PSCAD tutorial. In this tutorial we will see a simple sinusoidal pulse with modulated inverter system, and you can see that this is a six switch, means three phase voltage source inverter. Our voltage is given by the these capacitors, and this is the DC side and this is the AC side. AC side is connected with the power system. This is a grid, uh, this is a source, and it is connected through the transformer. Okay, and for the connection diagram is already you have studied in your power electronics books, and here switches are IGBT and corresponding gate pulse are given. And for this gate pulse, control logic, this is the control logic of sinusoidal pulse width modulation, SPWM. So here sinusoidal waveform is compared with the triangular waveform with a higher frequency, multiple of the fundamental frequency, and for uh, if we run this, it will be more clear. First run it. First we have to just we have to it is okay, it is running. Let the program and let the simulation run first. Okay, this running is complete. First we have to make a sinusoidal waveform. Sinusoidal waveforms for different phases. So for that, this is a sinusoidal waveform. This is a sinusoidal amplitude AM, FM, PM modulator, and we can make a sinusoidal waveform from this. And frequency is nothing but our fundamental frequency, that is 50 hertz. Okay, and phases are given. Phases means for a phase, and this is the phases. Suppose this is a 5-degree phase, started with a 5 degree. Okay, now this is our y. This is is 120 degree apart from this uh, red phase. This is y phase, and this is actually 120 degree minus, and this is a blue phase. This is 120 degree plus. Okay, so different phases are given to the sinusoidal waveform generator, and frequency is the same, and magnitude, say magnitude, we set at 0.9, and for the triangular pulse is magnitude of 1. So, and it is the for the triangular pulse, we need to multiply the fundamental frequency with certain frequency um, uh, to build a triangular pulse with higher frequency. So for that, this is the carrier frequency. This is a carrier waveform, and up to 10 position, it is multiplied by 27. Okay, you can also take higher values for this multiplying factor. This is actually multiplying factor, and this is the fundamental frequency. You can uh, multiply with 30 also. It will be this frequency will be modulated. And from that, this is a variable frequency sawtooth waveform, and we select maximum output level is 1 and minimum output level is -1. So the sawtooth waveform is look like a triangular waveform. If we put this is 0, then it will be a sawtooth waveform. Okay, and you can see that corresponding pulse, this is this triangular pulse, and sine 1 is nothing but this is the sine 1, and triangular means this. So, and pulse means the get pulse of the IGBT1 is this. Okay, this delay is given, a very low delay is given. You cannot if you want you can delete this one also. Okay, so this is the pulse generator. What is the logic? Actually, if the carrier waveform means our sinusoidal waveform is less than the uh, uh, sorry if the sinusoidal waveform means reference waveform is less than the carrier waveform, then it will give the pulse to the IGBT gate. Okay, so you can see from that instant that um, this in that position, if we maximize it. Okay, now this this is the reference if we can make boldly. Okay, this is our reference waveform is just less than the carrier waveform, so we get a pulse for the gate signal. Okay, and if we maximize it again, you can see that you can see the pulse variation, actually pulse with variation and pulse with modulation. So width of the pulse is important, so you can see that width are changing and it is different for every instant, and so that pulse with modulation can be possible. And this is the modulated pulse, and which is given to the IGBT 1, and IGBT 1 and 4 cannot energize at same instant as short circuit may happen. So for that, this gate IGBT gate signal 4 is just um, uh, you can say this is the NOT gate. Actually, NOT gate means gate 1 pulse, when the gate 1 pulse is 1 and the gate 4 pulse will be 0. So, and delay is given the same time, so this is the same time. You can avoid this delay also. So to avoid short circuit, IGBT for the gate pulse for IGBT 1 and 4, or IGBT 3 and 6, IGBT 5 and 2 cannot energize at the same instant. So this is a open loop control system, as we are mentioning the phases and magnitude by manual. So this is not a closed loop. We cannot take any reference to find the phases and magnitude for this SPWM technique. For that, we build another inverter set as active. This is an inverter, and you can see that if we go to the firing pulse generator, this is in the phases means angle and the magnitude. Oh, this is should be 50. Okay, run this. Okay, this angle and magnitude uh, should be okay. Okay, this is our P and Q active and reactive power. We can calculate from here from this multimeter. This is P and Q. Okay, and P and Q we have to take the base value for reference. So this is the base value. Base value is 200 MVA. We assume so 1 by 200 means 0.005, and we set a P reference, say initial value is this. Okay, initial value is this, and it will this signal and this signal subtracted, this signal is passed through a PI controller to minimize the error, and we get the angle signal from this. And similarly from the reactive power we get the magnitude, and which is this is the signal we fed to this magnitude and phases of the sinusoidal waveform generator, and the operation is rest of the operation is the same. So you can see that this is just look like the previous model, but the difference is it is a closed loop system, and where the magnitude and phases of the sinusoidal waveform generator is just taken from a closed loop control. Okay, so I think this is clear for this control logic of both open loop and closed loop system of a voltage source inverter. Okay, so this is the end of this tutorial. Thank you.